One of the problems that plagued aviation's pioneers was developing an efficient way of converting the power produced by the engine into useful thrust. With few exceptions, nearly all of the early practical designs used propellers to create the necessary thrust. Technology advanced rapidly during the early years of aviation. More efficient airplanes and engines demanded better performance from the propeller. The airplane's development as an instrument of war introduced a sense of urgency in the design of new types of propellers. Even today, new propeller designs increase the performance and comfort of aircraft powered by both gas turbine and reciprocating engines. Although very little field maintenance of propellers is performed, the well-informed maintenance technician must be aware of the operating principles of propellers and be able to determine if they are operating properly. This program on aircraft propellers has been prepared to familiarize the technician with the knowledge and skills required to assure continuous and safe operation of propeller systems. In part one of this program, we will discuss propeller nomenclature, theory of operation, and look at some different types of propellers and how they operate. In part two, we will examine what is involved in the inspection of a propeller system, look at some field repairs that are permitted, and take a brief tour of an overhaul facility. Before you can begin any detailed discussion of propeller theory, there are certain terms that must be added to your vocabulary. The blades, which are actually rotating airfoils, have a leading edge, trailing edge, tip, shank, and attached to the engine at the propeller hub. Many people have trouble with the terms blade back and blade face, so it may be helpful to visualize the flat side of the blade as facing the pilot in the cockpit. A term that will be used frequently is blade angle. This is the angle between the propeller plane of rotation and the chord line of the propeller airfoil section. Distance along the propeller blade is expressed in stations, measured in inches from the center of the propeller hub. Because a propeller blade is a rotating airfoil, it produces lift by aerodynamic action. The amount of lift produced depends on the airfoil shape, RPM, and angle of attack. Before discussing ways of varying the amount of lift generated by a propeller blade, it is necessary to understand some of the design characteristics. If the blade angle of a propeller were measured at each station along the blade, you would find that the blade angle near the shank would be the highest, with a decrease in angle toward the tip. This is known as pitch distribution and is necessary because each section is moving at a different velocity, with the slowest speeds near the hub. To illustrate the difference in speed, consider the propeller seen here. If the propeller is rotating at 1800 RPM, the 10-inch station will be traveling at 107 miles per hour, while the 20-inch station must travel at 214 miles per hour, and the 30-inch station moves at 321 miles per hour. The airfoil that gives the best lift at 107 miles per hour would be quite inefficient at 321 miles per hour, so the airfoil is changed gradually throughout the length of the blade. The angle of attack of a propeller blade section is the angle between the face of the blade and the relative wind, where the relative wind is a result of the combined velocities of rotational speed and airspeed. As a propeller rotates, many forces are interacting, causing stresses, which the propeller must be designed to withstand. The force which causes the greatest stress on a propeller is centrifugal force, which tries to pull the blades out of the hub. This force may be as much as 25 tons. Thrust bending force tends to bend the propeller blades forward at the tips, due to lift toward the tip of the blade, flexing the thin blade section forward. Torque bending force is the force which tends to bend the propeller blade back in the direction opposite to the direction of rotation. Aerodynamic twisting moment tries to twist the blade to a higher angle by aerodynamic action. This results from the center of rotation of the blade being at the midpoint of the chord line, while the center of pressure is more toward the leading edge of the blade. Centrifugal twisting moment tends to decrease blade angle. This is caused by all parts of a rotating propeller trying to move in the same plane of rotation as the blade center line. This force is greater than aerodynamic twisting moment and is used in some designs to cause a decrease in blade angle. Propeller blades are also subject to a number of vibratory stresses. By this we mean that a propeller blade will start to vibrate when it is excited by some external alternating force. If the frequency of this vibrational force coincides exactly with the natural vibrational frequency of the blade, resonance occurs. If a blade goes into resonance, it will be in a condition called a mode. When it vibrates in a mode, higher than usual stresses occur at the points where the blade is bending. These points are known as nodal points. Sometimes certain airplane, propeller, engine combinations produce a concentration of vibratory stresses at certain RPMs. Consequently, extended operation of the engine in this RPM range is prohibited. This is marked on the tachometer by a yellow arc or a red line. A nick in the area of a nodal point has the same effect as notching a piece of wire and flexing it back and forth until it breaks. The notch provides a focal point where stresses concentrate, causing the wire to break much more readily. The same thing can happen to a propeller, and for that reason it is wise to remove any nick or scratch which occurs on any part of the blade. Propeller pitch is the distance that a propeller will move forward in one revolution. This is more properly called geometric pitch and is theoretical in that it does not take into account any losses due to inefficiency. Effective pitch is the distance that an aircraft actually moves forward in one revolution of the propeller. Effective pitch may vary from 0 when the aircraft is on the ground to about 85% of geometric pitch during the most efficient flight conditions. The difference between geometric pitch and effective pitch is called slip. In the next section, we will take a careful look at many of the different types of propellers that have been used over the years. The fixed-pitch wooden propeller is the granddaddy of all aircraft propellers and is still being manufactured today. Wood propellers are lightweight and have less tendency to vibrate than metal propellers of the same power rating. Wooden propeller manufacturing starts with a blank of laminated wood, seen here at the rear of the cart. The wooden blanks are placed in a profiling lathe where a continuously rotating stylus copies the profile of the original master blade and transforms the blank into a nearly finished propeller. Hand carving is a job for expert craftsmen who will accept nothing short of perfection. Only years of experience and technical know-how can transform a simple block of wood into an efficiently operating and dynamically stable propeller. After hand carving and balancing, a tough armor coating of nitrate plastic, approximately 30 thousandths of an inch thick, is applied to each propeller. This coating is applied to only one half of the propeller at a time. Each half is allowed to cure for 24 hours before the second half is put on. Lap joints, where both ends of the coating come together, are hand scraped to a smooth and beautifully finished surface. Secondary balancing is accomplished before the stainless steel tipping is applied. Stainless steel tipping is hand-formed and secured with both rivets and screws to afford maximum strength and durability. With the screws and rivets secure, The propeller is now ready for the flushing operation. Each screw and rivet hole is filled with solder and ground flush by hand. Relief cuts are carefully spaced and calculated to ensure against random cracking due to blade flexing. Depending upon requirements, the propeller is either painted or varnished and finish balance accomplished. Although wood props are still being manufactured, most low horsepower aircraft use a fixed pitch metal propeller. These are usually manufactured from a single piece aluminum forging that has been shaped by machining and hand grinding to a propeller of the desired design. A fixed pitch aluminum prop has the advantages of being durable, resistant to weather, lightweight, requires a minimum amount of maintenance, and is simple to maintain. A fixed pitch propeller must be chosen to give the desired performance for only one set of circumstances. For example, a propeller designed to give optimum performance at cruise will result in an abnormally long takeoff run and slow climb, while a propeller that performs well at takeoff will result in a slow cruise speed. Ground-adjustable propellers are designed so that their blade angle can be adjusted on the ground to give the desired performance. The propeller is designed so that the blades can be rotated in the hub to change the blade angle. The hub is held together with clamps or bolts to prevent the blades from rotating during operation. Ground-adjustable propellers did not allow the flexibility of changing pitch in flight. One early design that allowed the pitch to vary during operation was the automatic pitch-changing propeller. Automatic propellers are designed so that the blade angle will change in response to operational forces as flight conditions change. At high power settings and low air speeds, as in climb, the propeller will respond by decreasing blade angle to provide good climb performance. There is no cockpit control as the propeller is an independent and automatic unit. The automatic propeller uses the natural forces acting on the blades and counterweights to achieve the desired change in blade angle. The automatic design in most common use is the Kopper's Aeromatic, which uses a laminated wood blade that has been coated with a black plastic for protection. The shank of each blade is mounted in a steel sleeve and attached to the hub. The installation of an aeromatic propeller is the same as for a fixed pitch propeller. When checking blade track, be sure that the blade is at full low or high blade angle. Remember, the blade path moves forward as blade angle decreases. Inspection, maintenance, and repair of an aeromatic propeller should be accomplished only in strict accordance with the manufacturer's recommendations. A controllable pitch propeller is designed so that the pilot can select any blade angle within the propeller's range at any time during the aircraft's operation. The controllable propeller is operated from the cockpit by a crank handle mounted on the instrument panel. When the crank handle is turned, a flexible cable turns a pinion gear mounted in a bracket directly behind the propeller, which meshes with a drive gear fitting around the crankshaft and mounted to the engine crankcase. The drive gear is mated to the actuator, which rotates the blades on the propeller. Some installations of controllable propellers may incorporate the use of an electric motor to move the drive gear, using only a simple toggle switch in the cockpit. A two-position propeller system is designed so that the pilot can select one of two blade angles in flight. This allows the pilot to select a low blade angle for takeoff and climb and a high blade angle for cruise. Two forces are used to cause the blade angle to change: engine oil pressure in the propeller cylinder and centrifugal force acting on the propeller's counterweights. The other operational forces have only a minimum effect on the system's operation. A selector valve is used to direct oil at engine system pressure or to drain the oil from the propeller and return it to the engine sump. The valve is controlled by the pilot from the cockpit with a propeller control lever. When the propeller control lever is moved forward to decrease the blade angle, the selector valve directs engine oil to the propeller cylinder. As oil pressure moves the cylinder forward, it overcomes the centrifugal force on the counterweights and the blades rotate to a lower angle. To increase blade angle, the cockpit control is moved rearward and the selector valve releases oil pressure from the propeller. The centrifugal force on the counterweights is now greater than the force of the oil pressure on the propeller cylinder, and the blades rotate to a higher blade angle. Although the two-position propeller represented a breakthrough, the need for continuous control through a wide range of operations was needed. The constant speed propeller was developed to fulfill those needs. A constant speed propeller system is one in which the propeller blade angle is varied by the action of a governor to maintain a constant system RPM. The action of the governor allows the RPM to be held constant with changes in engine power settings and aircraft speed. Constant speed systems are used on most modern, medium, and high-performance single-engine aircraft. Constant speed propellers use a fixed force to cause an increase or decrease in blade angle. This force may be a spring, centrifugal twisting moment, or centrifugal force acting on a counterweight. The force is termed fixed because it is always present during operation and must be overcome to change blade angle. The most commonly used variable force, which will cause change in blade angle opposite to the fixed force, is engine oil pressure. The oil pressure is varied by the governor as necessary to adjust the blades to the desired angle. The propeller governor is an RPM sensing device, which responds to a change in RPM by directing oil pressure to or releasing oil pressure from the propeller to change blade angle and return system RPM to the original value. The governor is set for a specific RPM by the cockpit propeller control. The basic governor consists of a drive shaft connected to the engine drive train and rotating at an RPM proportional to that of the engine. An oil pump drive gear is located on the drive shaft and meshes with an oil pump idler gear. This pump takes engine oil pressure and boosts it to propeller operating pressure. The boosted oil pressure is routed through passages in the governor to a pilot valve, which fits in the center of the hollow drive shaft. This pilot valve moves up and down and directs oil to or from the propeller to vary the blade angle. The position of the pilot valve is determined by the action of the drive shaft. When RPM increases, the flyweights tilt outward and raise the pilot valve, thus directing oil pressure to or away from the propeller, causing the propeller blade angle to change and the RPM to return to the selected value. The opposite is true when the RPM falls below the selected value. The movement of the flyweights is opposed by a speeder spring, which is located above the flyweights and is adjusted by the pilot by moving the propeller control in the cockpit. A constant speed propeller system uses the manifold pressure gauge to indicate throttle setting, and the tachometer is used to indicate the setting of the propeller control. It should be noted that it is possible to damage the engine if the manifold pressure is too high for a given RPM setting. Always refer to the aircraft's engine performance charts and operator's manual before operating the engine. Feathering propellers are used on all modern multi-engine aircraft. The primary purpose of a feathering system is to eliminate the drag created by a windmilling propeller when an engine fails. Feathering propeller systems are constant speed systems with the additional capability of feathering the propeller. This means that they have the ability to rotate the propeller blades to an approximate 90-degree blade angle. The cockpit propeller control lever incorporates an additional range of movement to allow feathering the propeller, or uses a separate push-button control to operate the feathering mechanism. Feathering operations are independent of constant speed operations and can override the constant speed function to feather the propeller at any time. Since the propeller governor gets its supply of oil from the engine lubrication system, any time that engine oil pressure is lost through a broken line, seal, excessive oil consumption, or for any other reasons, the propeller will automatically feather in many systems. If loss of oil pressure causes automatic prop feathering, why doesn't the prop feather when the engines are shut down on the ground? As long as the propeller is rotating at speeds over 800 RPM, centrifugal force acts to disengage spring-loaded latches, thereby allowing the propeller to enter the feathered position. At lower speeds or when the engine is stopped, these spring-loaded latches engage, thereby preventing the propeller from going into the feathered position. Unfeather in most systems is accomplished by moving the propeller control to the normal flight range and restarting the engine. As soon as the engine cranks over a few turns, the governor oil pressure builds up. This overcomes spring tension and the governor starts to unfeather the blades. Windmilling then takes place and speeds up the unfeathering process. Some feathering systems may incorporate the use of an unfeathering accumulator to provide oil pressure to unfeather the propeller. A reversing propeller is a constant speed feathering propeller with the additional capability of providing reverse thrust. These are used on many modern turboprop aircraft. Reversing propellers have the advantage of decreasing landing roll, reducing brake wear, and increasing ground maneuverability. The main disadvantage of the reversing system is the reduction of engine cooling available for piston engine aircraft and the increased blade damage from stones and sand when the propeller is in reverse. When a propeller goes into reverse, the blades rotate below the low blade angle and into a negative angle of about -15 degrees. This forces air forward to provide negative thrust. The reversing operation is controlled in the cockpit by the throttles and is initiated by moving the throttles aft of the idle position. The further aft the throttles are moved, the greater the reverse thrust. Propellers cannot normally be reversed in flight, and the aircraft must often be below a specified speed on the landing roll before the props can be reversed. Many systems require that the aircraft wait be on the landing gear before the throttles can be moved into the reverse range. This is controlled by a squat switch on the landing gear strut. As you have seen, there are many different types of propeller systems being used. Some are very old designs, and some reflect the most modern of technology. Each of them have the same goal: to provide the most efficient thrust possible for a given set of conditions that may include engine horsepower, weight, cost, and aircraft performance requirements. Only by understanding the operating principles of these propeller systems can the technician accurately analyze a system malfunction and recommend a course of action. Part 2 of this program will examine what is involved in the inspection of a propeller system, look at some field repairs that are permitted, and take a brief tour of a propeller overhaul facility. has been said many times that the total machine is only as good as its parts. The airplane is no exception. The safe, reliable operation of an aircraft is dependent on each of its components functioning properly. One very important component is the propeller. This is the unit that converts the power of the engine into usable thrust. Proper inspection and maintenance of the propeller will assure you of continued reliable operation. To assist the technician in understanding propeller operation and care, this program on aircraft propellers has been prepared. In part 1 of this program, we discussed propeller nomenclature, theory of operation, and looked at some different types of propellers and how they operate. In this part, we will examine what is involved in the inspection of a propeller system, look at some field repairs that are permitted, and take a brief tour of an overhaul facility. Part of every inspection of an aircraft should include checking the condition and operation of the propeller system. Before you begin a propeller inspection, it is necessary to be able to interpret the manufacturer's model designation number. This number is the key to locating data that will pertain to the particular propeller installation. Aircraft propellers must be certificated under FAR Part 35 and must contain the following information on the hub or butt of the propeller blades: manufacturer's name, model designation, serial number, type certificate number, and production certificate number. The method of interpreting model designations will vary with manufacturers, but they will be similar to the one shown here. The code 1A90 is the basic model. The DM indicates the type of crankshaft that the propeller will fit, blade tip contour, adapter used, and provides other information pertaining to the specific installation. The 76 is the diameter of the propeller in inches, and the 51 is the pitch of the prop at the 75% station. Constant speed propellers are usually identified by a code number for the hub and another for the blades. A typical blade designation is seen here, listing the blade diameter, basic model number, and variations in length from the basic diameter. This is a hub model designation, and it is interpreted as shown here. The information includes the type of propeller, basic design, number of blades, blade shank size, the type of crankshaft the hub will fit, and a code for special design features or modifications. Make certain that you are familiar with the particular code used by the manufacturer of the propeller that you are inspecting. Details of these codes can be found in the type certificate data sheet for the propeller. The equipment list for the aircraft that you are inspecting should include the make and model of propeller installed on the aircraft. Always check to see that the model installed matches the propeller shown on the equipment list. The type certificate data sheet for the airplane will list the propellers that have been approved for installation on that particular aircraft. Propeller type certificate data sheets will often list some engine propeller combinations that have been approved by the propeller manufacturer. This information will be found in Note 9 of the data sheet. The summary of supplemental type certificates may list additional propellers that have been approved for a particular aircraft. These will be found under the listing for the aircraft's manufacturer and model number. The inspection, adjustment, installation, and minor repair of a propeller and its related parts are the responsibility of the power plant mechanic. The power plant mechanic may also perform the 100-hour inspection of the propeller and related components. Major repairs, alterations, and overhauls of propellers must be done by the manufacturer or a certified repair station. The 100-hour inspection of the propeller system should be accomplished in accordance with the instructions outlined by the aircraft manufacturer. If there are no specific instructions supplied, The inspection may be accomplished according to FAR Part 43, Appendix D. Control systems should be checked for defects, improper travel, and improper safety. Lines, hoses, and clamps must be inspected for leaks, improper condition, and looseness. Accessories for apparent defects in security of mounting. The propeller assembly must be checked for cracks, nicks, binding, and oil leakage, bolts for improper torquing, and lack of safety. Anti-icing and de-icing systems should be checked for improper operation and obvious defects. Constant speed propellers may call for periodic lubrication. This should only be accomplished in strict accordance with manufacturer's service information. Caution: improper lubrication of propellers could result in damage to hub seals. Small nicks in propeller blades may be repaired by the technician in the field. Extreme caution should be observed to assure an airworthy repair. Before attempting a repair, the proper equipment should be assembled. These tools may be gathered from stock sources or purchased in a kit like the one seen here. Either way, the files and other tools used for a propeller repair should not be used for any other job. The type of repair will be determined by the severity of the damage to the propeller blade. For demonstration purposes, we will use a propeller with moderate damage. Damage to the leading edge should be smoothed out across an area that is 10 times the depth of the nick. Damage to the propeller face should be smoothed out across an area 20 times the depth of the damage. A final determination must be made according to the propeller manufacturer's recommendations. For this initial step, a course file is used to remove the damage. When the local repair of the blade is finished, the blade should be reshaped to its original configuration. Draw a file along the length of the blade with a fine file. As you shape the edge, make sure that it is returned to the original thickness of the leading edge. Once filing is completed and the blade has been returned as closely as possible to the original shape, the repaired area must be further smoothed by careful sanding. All file marks must be removed as they are potential stress areas. In order to determine if all of the damage has been removed and no cracks exist, a simple dye-penetrant inspection may be used. Before applying the penetrant, carefully clean the area to be checked. Use clean solvent and a soft cloth. Apply the penetrant according to the directions and wait the specified dwell time. Remove the penetrant by wiping the blade with a clean, dry cloth. After most of the penetrant has been removed, wipe with a clean cloth moistened with solvent. Apply the developer according to instructions and allow at least 2 minutes for developing time. As the developer dries to a smooth white coating, red indications will appear at the location of cracks and defects. If any cracks appear, repeat the filing procedure and check the blade again. If a crack is discovered that cannot be removed, the propeller must be removed from service before further flight. The propeller should be sent to a certified propeller repair station for evaluation and possible repair. In order to better understand what happens when a propeller is sent to an FAA-approved repair station for overhaul, let's take a brief tour of a large propeller overhaul facility and examine each of the steps in propeller overhaul. By examining this flow chart, you can begin to realize some of the complexities of propeller overhaul. We have outlined here the many steps that a constant speed propeller must go through during overhaul. When a propeller is received for overhaul, it is necessary to identify all current specifications, service bulletins, airworthiness directives, and general information that may have been published by the manufacturer of the propeller. The serial number is checked, and notes are made of the condition in which the propeller was received. A propeller service status form is filled out to identify the propeller and detail the customer's orders for the repair. On this form is entered the condition of the blades and hub upon receipt. This report is also used periodically to check the progress of a particular propeller, wherever it may be in the overhaul process. During the pre-teardown inspection, documents are carefully reviewed and an accurate measurement of blade angles and track are taken and recorded on an FAA-approved form. As the propeller is disassembled, all related parts are inspected and recorded on the overhaul record. The parts are placed in small component trays where they will remain with the major structural pieces of the propeller as they move through the overhaul. Many specialized tools and fixtures are required in the disassembly of some propellers. Here, a 12-foot torque bar is being used to remove the blade of a Macaulay constant-speed propeller. The torque required here may go as high as 1,500 foot-pounds. After disassembly, areas that show excess wear or discoloration can be examined more closely to determine their serviceability. After disassembly, cleaning, and inspection, the component parts of each propeller go their separate ways. After completing their separate routes, they will be brought together again in the final assembly and inspection portion of the overhaul. Non-ferrous components of the hub are inspected for cracks using dye-penetrant inspection. Here the parts are immersed in the penetrant solution, then washed and blown dry with warm air. A powder developer is applied to the part to draw any of the penetrant that has been retained in a crack to the surface. Under an ultraviolet inspection lamp, the penetrant drawn from the crack will be clearly visible as a fluorescent line. Magnetic particle inspection is used to locate discontinuities in ferrous metal parts. The steel parts of the propeller are magnetized by passing a strong electrical current through them. A suspension of fluorescent iron oxide powder and solvent is sprayed over the parts. The particles within the fluid will immediately align themselves with the discontinuity. When examined under black light, a crack or fault will show as a fluorescent line. The rework and bead blast of the hub and its components are the final steps before plating and assembly. Bead blasting utilizes small glass beads shot from an air gun. This process will remove all traces of scale, corrosion, and foreign materials. All parts of the hub manufactured from ferrous metals are cadmium plated. This plating offers the maximum protection against corrosion in the elements. Cadmium plating is done in this room. Precision instruments are used to monitor the process, and the solution is tested for purity at regular intervals. In this oven, cadmium-plated parts are baked at 350 degrees for a period in excess of 3 hours. This procedure drives off the hydrogen atoms within the metal surfaces. This will eliminate the possibility of future metal crystallization and component failure. The hub components are now ready for reassembly. Let's leave them and go back to follow the blades through their overhaul process. The first step in blade overhaul is the precision measurement of blade width, thickness, face alignment, blade angles, and track. Blade width is accurately checked with a vernier caliper at stations along the length of the blade. These dimensions are specified by the propeller manufacturer. Thickness measurements are also taken along the same specified intervals. Measurements are recorded and double-checked against the manufacturer's overall specifications. Blade track is checked and recorded. Blade repair, for the most part, involves blade straightening, filing, grinding, and repitching if necessary. This photograph identifies a repairable blade. The manufacturer's specifications dictate certain allowable limits from which a damaged blade may be straightened and returned to airworthy condition. The blade seen at the top of the picture is repairable. The blade at the bottom is not. Damage limitations are depicted on graphs like the one seen here. These are supplied by the propeller manufacturer. This graph identifies the amount of bend allowed in any 2-inch section of the blade. The arrow shows that this manufacturer will tolerate a 13.4-degree bend at a distance of 28 inches from the hub. A damaged propeller blade may be straightened using large hydraulic presses. Despite the first impression one may get, this is an accurate and carefully controlled process. Specialized tooling and precision measuring equipment permit the repair station to make pitch changes or corrections as small as 1/10 of 1 degree. Face alignment and angle measurements are taken once again to ensure accuracy. This constant checking throughout the straightening and blade angle change will ensure perfection in the finished product. Eddy current inspection is used in critical areas of the blade. This procedure is now required by an airworthiness directive on several models of propeller blades. Shot peening is a process that uses hardened steel balls shot from a pneumatic gun against the propeller blade. This is used in the shank area of the blade to ensure maximum strength of the surface of this dynamically stressed component section. Grinding and polishing is the last step in the blade reconditioning. Precision hand grinding removes all corrosion, scratches, and burrs prior to the anodizing process. Close visual inspection is used to detect any small pits and scratches that could lead to blade failure. Anodizing aluminum propeller blades protects them from weather and avoids corrosive buildups that could lead to blade failure. With both the hub and the blades having completed their respective overhaul processes, the propeller is ready for final assembly. The propeller components are carefully laid out and made ready for assembly. Part numbers are rechecked with the manufacturer's specifications. Each part is checked for cleanliness and the parts are lubricated. After final assembly, constant speed propellers are checked for proper operation by connecting them to a pneumatic test stand and cycling the propeller through its blade angle range. The assembled propeller is checked for static balance using this knife-edge device. Small amounts of lead wool or steel weights are placed in the hub areas of each blade to bring about perfect balance, both horizontal and vertical. As with most aircraft components, all of the hardware on the propeller assembly must be safetied. This will prevent inadvertent loosening of the fasteners. Paint and decals are applied to the propeller at this point. By using the original manufacturer's decals and paint schemes, the propeller is brought back to a factory-new appearance. The final inspection makes certain that the propeller is airworthy and ready for use. Once again, the safety wire is checked and the maintenance release tags are filled out. These tags are attached to the propeller and serve in lieu of Form 337 to certify that the major repairs or alterations have been made and the propeller is returned to service. The propeller is now ready for crating and shipping. This must be accomplished very carefully to avoid shipping damage. Let's take another brief look at the flow chart. We have followed a propeller through each of the 23 steps outlined here. It can be easily seen that propeller overhaul is a precise skill, requiring many specialized tools and machines. The maintenance technician should develop a good working relationship with the prop shop in order to better serve the customer. Although the propeller is one of the most trouble-free components of an aircraft, the system does require the maintenance technician to have a basic understanding of its operation, the ability to recognize trouble when it does up the skills to make minor repairs, and the wisdom to know when to send the propeller to a certified repair station for overhaul. Application of these basic principles can assure the operator of many trouble-free hours of service from his aircraft.